Listening Practice, Chapter 1, Introduction to Modern Space Technology. The 21st century has ushered in a transformative era for space exploration, marked by rapid technological advancements, unprecedented collaboration, and fierce competition. Once dominated by Cold War-era superpowers, the cosmos is now a frontier where private enterprises, startups, and nations alike vie for breakthroughs that promise to redefine humanity's relationship with space. This chapter explores the foundational shifts driving modern space technology, from its historical roots to the dynamic interplay of innovation, ambition, and economics shaping its future. 1.1 The evolution of space exploration. Space exploration has evolved from symbolic milestones like the launch of Sputnik, 1957, and the Apollo moon landings, 1969-1972, to today's pragmatic focus on sustainability and scalability. Early programs prioritized national prestige and scientific discovery, but modern efforts aim to establish permanent infrastructure such as lunar bases, Mars habitats, and satellite megaconstellations that supports both exploration and commerce. Key turning points include the Shuttle era. 1981-2011 reusable spacecraft demonstrated the potential for cost reduction, albeit with limitations. Rise of private ventures, 2010 SpaceX's Falcon 9 landings, 2015 onward, proved reusability's viability, disrupting traditional aerospace economics. Artemis and beyond, 2020's government programs now partner with private firms to return humans to the moon and prepare for Mars. This evolution reflects a shift from episodic missions to sustainable, economically viable systems. 1.2 Key players in the 21st century space race. The modern space race is no longer a binary contest but a mosaic of stakeholders, government agencies, NASA, U.S. leading Artemis, CLPS, and Mars sample return missions, ESA, Europe developing reusable rocket prototypes, e.g., Themis, and lunar logistics, CNSA, China expanding its Tiangong space station and lunar rover programs. Private giants, SpaceX, dominating launch markets with Starship and Starlink. Blue Origin, advancing New Glenn and lunar lander technologies. Startups, Relativity Space, pioneering 3D printed rockets, Terran 1, Terran R. Rocket Lab, democratizing small satellite launches with Electron. Collaborative ventures, partnerships like NASA's Commercial Crew Program and Axiom Space's private modules for the ISS. This diversity fuels innovation but also raises questions about regulation, safety, and equity in space access. 1.3 The role of private companies versus government agencies. The line between public and private space endeavors has blurred. While governments once held a monopoly, private firms now drive cost reduction and rapid iteration. Government strengths, funding high-risk, long-term science, e.g., James Webb Space Telescope. Establishing international treaties and regulatory frameworks. Private sector advantages, agile development cycles, e.g., SpaceX's iterative Starship prototypes. Commercial models, e.g., satellite broadband, space tourism. Case studies in synergy. NASA's Artemis program relies on SpaceX's Starship for lunar landings and Blue Origin's Blue Moon lander. Relativity Space's Terran 1 leveraged NASA test facilities and FAA approvals despite its private funding. However, tensions persist. Critics argue privatization risks prioritizing profit over safety, environmental stewardship, or equitable access. Meanwhile, governments struggle to balance innovation with oversight, exemplified by FAA investigations into launch failures like Terran 1's 2023 anomaly. Chapter 1 Summary. Modern space technology thrives on a paradox: competition accelerates progress, but collaboration remains essential for humanity's grandest ambitions. As reusable rockets, 3D printing, and AI redefine possibilities, the interplay between private ingenuity and public oversight will determine whether we build a sustainable off-world future or repeat the mistakes of Earth's resource races. The following chapters delve into the technologies, triumphs, and trials defining this new era. Chapter 2, Historical Foundations of Rocketry. The story of space technology is rooted in centuries of scientific inquiry, wartime innovation, and Cold War rivalry. From the rudimentary gunpowder rockets of ancient China to the towering Saturn V that carried humans to the moon, rocketry's evolution reflects humanity's relentless drive to conquer the skies and beyond. This chapter traces the pivotal breakthroughs, visionary engineers, and geopolitical forces that laid the groundwork for today's reusable rockets and interplanetary ambitions. 2.1 From Sputnik to the Space Shuttle. The mid-20th century marked rocketry's transition from speculative science to a tool of global power. Key milestones include V-2 rockets, 1940s, developed by Nazi Germany. These were the first long-range guided ballistic missiles. Post-World War II, captured V-2s, and engineers like Wernher von Braun jump-started US and Soviet programs. Sputnik 1, 1957. The Soviet Union's beach-ball-sized satellite ignited the space race, proving orbital flight was possible and triggering US panic over the missile gap. Apollo program, 1961-1972. Fueled by Cold War rivalry, NASA's Saturn V rocket, still the most powerful ever flown, delivered astronauts to the moon. Space Shuttle, 1981-2011. A hybrid spacecraft rocket, the Shuttle promised reusability but suffered from high costs and tragedies like Challenger, 1986, and Columbia, 2003. Legacy: these programs proved the feasibility of large-scale rocketry but relied on disposable systems. The Shuttle's partial reusability, recovering orbiters and reusing solid boosters, hinted at future innovations but fell short of cost-saving goals. 2.2 The rise of reusable rocket concepts. Reusability emerged as a holy grail to reduce launch costs and enable frequent access to space. Early concepts faced technical and cultural resistance. DCX, 1990s. NASA's experimental vertical takeoff, vertical landing rocket demonstrated controlled descent but was cancelled due to budget cuts. SpaceX's Grasshopper, 2012-2013. This prototype validated autonomous landing algorithms, paving the way for Falcon 9's first stage recoveries starting in 2015. Space Shuttle's lessons: despite recovering orbiters, refurbishing heat shields and engines proved more expensive than building new rockets, a cautionary tale for modern engineers. Modern paradigm shift: Falcon 9 Block 5, designed for 10+ flights per booster, it reduced launch costs by 60% and normalized reuse. Starship's full reusability: SpaceX's stainless steel behemoth aims to refuel in orbit and land on Mars, treating rockets less like fireworks and more like airplanes. Reusability's success hinges on rapid turnaround, durable materials, and economies of scale, principles now adopted by competitors like Rocket Lab, recovering electron boosters via helicopter. 2.3 Material science breakthroughs in aerospace. Rocketry's progress is inseparable from advances in materials that withstand extreme heat, pressure, and radiation. Aluminum lithium alloys, 1960s. Present lightweight and strong, these alloys dominate fuel tanks and airframes, e.g., Space Shuttle external tank. Carbon-carbon composites, used in SpaceX's Starship heat shield and Space Shuttle leading edges, they endure re-entry temperatures exceeding 1,600 degrees Celsius. Additive manufacturing, 2010's. Present Relativity Space's 3D printed Terran 1 replaced thousands of welded parts with single printed structures, slashing production time and failure points. Methane propulsion: companies like SpaceX and Relativity favor methane engines, Raptor, Ian, for cleaner combustion and Mars compatibility, where methane can be synthesized from local resources. The future: self-healing ceramics, graphene-enhanced composites, and in-orbit manufacturing could further revolutionize rocket durability and performance. Chapter 2 Summary: the 20th century's expendable rockets were marvels of engineering but economically unsustainable. Today's reusable systems and advanced materials owe their existence to decades of trial, error, and incremental progress, from the V2's destructive origins to the Shuttle's unfulfilled promises. As modern innovators build on this legacy, they confront a critical question: will the lessons of history guide us toward a multiplanetary future, or will old pitfalls resurface in new forms? The next chapters explore how today's pioneers are answering that question. Chapter 3, SpaceX Starship, Redefining Space Travel. The SpaceX Starship represents a quantum leap in aerospace engineering, combining audacious design, full reusability, and a vision to make interplanetary travel routine. This chapter dissects its revolutionary architecture, analyzes its 2023 test campaign, and explores its potential to transform humanity's reach in the solar system while grappling with the economic and environmental ramifications of its ambition. 3.1 Design and engineering of a fully reusable system. Starship's design rejects decades of aerospace convention, prioritizing rapid reuse over disposable efficiency. 3.1.1 The Raptor engine, powering the Starship, full-flow staged combustion. The Raptor is the first methane-fueled engine to use the cycle, where both fuel and oxidizer preburners feed into the main chamber, maximizing efficiency, ISP 380 seconds, and reducing turbine wear. Methane advantage: unlike traditional RP1 kerosene, methane burns cleaner, minimizes coking, carbon buildup, and can be synthesized on Mars using CO and water ice, in situ resource utilization. Scalability: Starship's Super Heavy booster houses 33 Raptors, generating 16.7 million pounds of thrust, nearly double the Saturn V's. 3.1.2 Stainless steel versus traditional materials, thermal resilience. SpaceX abandoned carbon composites for 301 stainless steel, which retains strength at cryogenic temperatures and withstands re-entry heat, up to 1,500 degrees Celsius, without ablative coatings. Cost and speed: steel is 50x cheaper than carbon fiber, enabling rapid prototyping. The shift also simplified welding techniques, though early prototypes struggled with weight until advanced alloys, e.g., 304L, were adopted. Trade-offs: steel's density requires innovative structural engineering, e.g., chins for aerodynamic control, to offset mass penalties. 3.2 Milestones in 2023, orbital test flights and outcomes. SpaceX's test, fail, iterate approach defines Starship's 2023 campaign, with 4 orbital attempts. 3.2.1 Flight dynamics and landing challenges. Launch profile: Super Heavy's 33 engines lift Starship to 65 km, followed by hot staging, igniting Starship's engines before booster separation. Belly flop maneuver: during re-entry, Starship pivots horizontally to maximize drag, then executes a last-second flip to vertical for landing, a maneuver requiring pinpoint Raptor throttling and fin control. Booster recovery: Super Heavy attempts a controlled descent to a virtual catch tower, but 2023 tests ended in explosions due to engine failures. 3.2.2 Data from successful and failed attempts. April 20, first integrated flight, destroyed after losing thrust vector control. Key lesson: pad shielding insufficient to prevent debris. November 18, second flight achieved stage separation but triggered automatic termination during Starship's burn. Progress included upgraded water deluge system and hot staging. Post-flight iterations: modifications included electric thrust vector controls, reinforced fuel tanks, and redesigned heat shield tiles. 3.3 Implications for lunar and Mars missions. Artemis program: NASA selected Starship as the Human Landing System, HLS, for Artemis 3. Its 100-plus ton payload capacity could deliver habitats, rovers, and ISRU equipment to the Moon. Mars colonization: Starship's 100-passenger capacity and Methalox refueling in Earth orbit enable cargo fleets to Mars. On Mars, methane production via the Sabatier process could fuel return trips. Deep space logistics: Starship's volume, 1,000 m superscript 3, supports multi-year missions, with potential roles in asteroid mining or orbital megaprojects. 3.4 Environmental and economic impact of reusability. Cost revolution: Full reusability aims to slash launch costs from $1,500/kg to $10/kg, democratizing access to space. Emissions dilemma: while methane burns cleaner than RP-1, a single Starship launch emits 2,500 tons of CO. Problematic at scale. SpaceX counters with pledges to use carbon-neutral methane. Market disruption: traditional aerospace firms face pressure to adopt reusable designs, while startups leverage Starship's low costs to deploy satellite constellations or space hotels. Chapter 3 Summary: Starship is more than a rocket, it's a paradigm shift. Its stainless steel hull and methane engines address the flaws of past systems, while its iterative development mirrors Silicon Valley's fail-fast ethos. Yet challenges remain: scaling reuse without compromising safety, mitigating environmental impacts, and proving its viability as humanity's interplanetary workhorse. As SpaceX races toward Mars, the lessons of 2023's fiery tests may well determine whether Starship becomes a footnote or a foundation for our multiplanetary future. Chapter 4 Relativity Space Terran 1, the 3D printed revolution. Relativity Space's Terran 1 represents a radical departure from traditional aerospace manufacturing, leveraging additive manufacturing, 3D printing, to streamline production, reduce costs, and accelerate innovation. While its March 2023 debut launch fell short of orbit, the mission underscored the transformative potential and growing pains of 3D printed rocketry. This chapter examines Terran 1's design, its historic launch attempt, and the roadmap for scaling this technology into humanity's next chapter of space exploration. 4.1 Additive manufacturing in aerospace. Relativity Space's core thesis is simple: 3D printing can compress years of production into months. 4.1.1 The Stargate 3D printer, technology overview: world's largest metal 3D printer, Stargate uses directed energy deposition, DED, where robotic arms melt aluminum alloy wire with lasers, layer by layer. Printing rockets in days. Terran 1's airframe was printed in under 60 days, consolidating thousands of parts into fewer than 1,000 printed components. Adaptive design: software-driven iterations allow real-time adjustments to prints, bypassing traditional tooling delays. 4.1.2 Cost efficiency and rapid prototyping, labor and waste reduction: 3D printing eliminates 95% of welding and machining, cutting labor costs and material waste. Faster failure: Relativity iterated through 400+ engine tests in 24 months, a pace impossible with traditional supply chains. Scalability: Stargate's modular design supports printing larger structures for Terran R and beyond. 4.2 Development of Terran 1. Terran 1, a small-sat launcher, was designed to validate Relativity's manufacturing approach while targeting the booming LEO satellite market. 4.2.1 EN engines and methane-based propulsion: EN1 engine, a 3D printed, gas generator cycle engine using liquid oxygen and liquid methane, methalox. Thrust: 23,000 lbf, sea level. Reusability potential: methalox's clean combustion enables easier refurbishment than kerosene engines. Mars compatibility: methane can be synthesized on Mars, aligning with long-term in-situ resource utilization, ISRU, goals. 4.2.2 Lightweight structures and aerodynamics: lattice structures, 3D printing enabled internal grids that reduce weight without sacrificing strength. Aerospike nozzle: Terran 1's unique nozzle design optimized performance across varying atmospheric pressures. Second stage innovations: a printed copper alloy combustion chamber survived extreme temperatures in static fire tests. 4.3 The March 2023 launch, analyzing the attempt. Terran 1's maiden flight from Cape Canaveral on March 23, 2023, marked the first orbital launch attempt of a 3D printed rocket. 4.3.1 Technical hurdles and flight anomalies: first stage success, the 9 EN1 engines fired nominally, achieving max Q, maximum aerodynamic pressure, a key test objective. Second stage failure: after stage separation, the second stage engine failed to ignite due to a software glitch in the ignition sequence. Data harvest: sensors confirmed printed structures withstood vibration, heat, and pressure loads, validating the airframe's durability. 4.3.2 Lessons from failure: software overhaul, Relativity revised ignition sequencing and added redundancies to the Terran R design. Public relations win: despite the anomaly, the launch demonstrated 3D printing's viability under flight conditions, attracting investor and customer confidence. 4.4 Future of 3D printed rockets, Terran R and beyond. Terran R, Relativity's fully reusable, medium-lift rocket aims to compete with SpaceX's Falcon 9. Payload: 33,500 kilograms to LEO, versus Terran 1's 1,250 kilograms. 3D printed reusability: printed aerospike engines and heat shields designed for 20-plus flights. On-demand manufacturing: Relativity plans mobile Stargate printers for off-world production of habitats and fuel depots. Industry disruption: competitors like Rocket Lab and Airbus now invest in 3D printing, but Relativity's vertically integrated approach, printing 95% of the rocket in-house, remains unique. Chapter 4 Summary: Terran 1's successful failure proved 3D printed rockets could survive the rigors of launch, but scaling the technology requires overcoming new challenges from engine reliability to regulatory hurdles. As Terran R takes shape, Relativity Space seeks to redefine not just how rockets are built, but where they're built, from Earth's factories to Martian workshops. Whether 3D printing becomes the standard for deep space infrastructure or a niche solution, its impact on speed, cost, and design freedom is undeniable, a testament to the audacity of reimagining aerospace from the ground up. Chapter 5: Regulatory and Safety Challenges. As space technology accelerates, regulatory frameworks and safety protocols struggle to keep pace. The rise of private launches, mega-constellations, and interplanetary ambitions has exposed gaps in governance, risk assessment, and ethical accountability. This chapter examines the balancing act between fostering innovation and safeguarding people, ecosystems, and the orbital environment, a tension that will define humanity's expansion into space. 5.1 FAA and International Launch Approvals. The U.S. Federal Aviation Administration, FAA, oversees commercial launch licensing, but its processes were designed for an era of infrequent government-led missions. Today's challenges include: environmental reviews. Starship's 2023 launch attempts were delayed by lawsuits over debris impacts on local wildlife, highlighting tensions between rapid iteration and ecological protection. Airspace coordination, with 180-plus launches in 2023, versus 70 in 2015, the FAA faces bottlenecks in managing airspace closures and collision risks. International compliance. The Outer Space Treaty, 1967, requires nations to authorize and supervise private launches, but enforcement is fragmented. Case study: Rocket Lab's Electron launches from New Zealand adhere to both national space laws and US ITAR, International Traffic in Arms regulations, export controls. Reform efforts. The FAA's Part 450 rule streamlines licensing for reusable rockets. The EU's Space Traffic Management Initiative proposes a unified debris tracking system. 5.2 Risk management in public and private missions. Risk tolerance varies dramatically between stakeholders. Public agencies, NASA's Class A missions, e.g., crewed flights, enforce failure probabilities below 1 in 270, requiring exhaustive testing. Private companies. SpaceX's test fly fix approach accepts higher risks for uncrewed prototypes, as seen in Starship's explosive 2023 tests. Insurance realities. Satellite operators pay premiums of 5–15% of mission costs, but insurers increasingly exclude coverage for untested vehicles like Terran R. Governments often underwrite high-risk missions, e.g., NASA's $4.2 billion indemnification for SpaceX's Crew Dragon. Emerging threats. Collision cascades. Kessler syndrome. Megaconstellations like Starlink, 42,000 plus planned satellites, raise orbital debris risks. Crewed mission liability, Artemis astronauts signing NASA's informed consent waivers highlight legal gray areas in deep space accidents. 5.3 Ethical considerations in rapid innovation. The move fast and break things ethos of Silicon Valley clashes with space's unforgiving nature. Planetary protection, SpaceX's Mars ambitions risk contaminating pristine environments with Earth microbes. Current NASA protocols lack enforcement power over private entities. Labor practices, critics allege SpaceX's aggressive timelines contribute to worker injuries at Starbase, Texas. Equity and access, satellite constellations could monopolize bandwidth, disadvantaging developing nations. Space tourism, $450K and per seat, raises questions about prioritizing luxury over scientific or public benefit. Militarization, private satellites like Maxar's imaging constellation are dual-use, aiding both disaster response and military targeting. Ethical frameworks in progress, the Montreal Declaration for Responsible Space Exploration, 2022, urges transparency and sustainability. The UN's long-term sustainability guidelines address debris mitigation but remain non-binding. Chapter 5 Summary, Regulation and ethics are the guardrails of the new space age. While agencies like the FAA adapt to privatized launches, global consensus on debris, safety, and equity remains elusive. The stakes are existential. Unchecked orbital congestion could render space unusable, while ethical missteps risk replicating Earth's inequalities on other worlds. As companies like SpaceX and Relativity push boundaries, society must answer, who gets to make the rules and who gets left behind? The next chapters explore how collaboration and competition shape this contested frontier. Chapter 6, International Collaboration and Competition. The global space arena is a dynamic interplay of alliances and rivalries, where nations and corporations vie for technological supremacy while grappling with the necessity of cooperation. This chapter explores how programs like NASA's Commercial Lunar Payload Services, CLPS, China's ambitious missions, and agile startups are reshaping the geopolitical and economic landscape of space exploration. 6.1 NASA's Commercial Lunar Payload Services, CLPS, NASA's CLPS initiative, launched in 2018, epitomizes the shift toward public-private partnerships in lunar exploration. By contracting commercial entities to deliver payloads to the Moon, NASA aims to reduce costs and accelerate timelines for the Artemis program. Key players, Intuitive Machines, landed the Nova-C spacecraft in 2023, delivering NASA instruments to study lunar regolith. Astrobotic, despite Peregrine's propulsion failure in 2024, its mission demonstrated commercial viability for lunar logistics. Firefly Aerospace, awarded a CLPS contract to deliver a seismometer and communications nodes. Impact on Artemis, CLPS missions provide critical infrastructure, e.g., power systems, navigation beacons, for sustained lunar presence. Challenges, balancing cost-saving commercial models with mission-critical reliability, as seen in mixed CLPS success rates. 6.2 China, ESA, and Emerging Space Programs. China, CNSA, Lunar Ambitions, the Chang'e 6 mission, 2024, returned samples from the Moon's far side, advancing plans for a lunar base by 2035. Tiangong Space Station, fully operational since 2023, hosting international experiments but restricted by U.S. trade laws, ITAR. Mars and Beyond, Tianwen-3, 2028, aims to return Mars samples, positioning China as a direct competitor to NASA ESA collaborations. European Space Agency, ESA, ExoMars partnership with Russia, suspended in 2022 due to geopolitical tensions, delaying the Rosalind Franklin rover's search for Martian life. Ariane 6, set to debut in 2024, Europe's answer to SpaceX's dominance in the launch market. Emerging programs, India, ISRO Chandrayaan-3's 2023 lunar landing solidified its role. American Samoa, a low-cost innovator. UAE, the Hope probe, 2021, and Rashid 2 rover, 2024, underscore ambitions to lead Arab world space initiatives. Geopolitical tensions, U.S.-China rivalry stifles collaboration, while ESA navigates reliance on U.S. partnerships and autonomous ambitions. 6.3 The role of startups in global space economies. Startups are disrupting traditional space economies with agility and niche innovations. Market niches. Rocket Lab specializes in small-sat launches via Electron and Lunar Photon spacecraft. Satellogic, Argentina provides hyperspectral Earth observation for agriculture and climate monitoring. Skyroot Aerospace, India developed Vikram S, the nation's first privately built rocket, 2022. Collaborative ecosystems, startups like iSpace, Japan, and SpaceX partner with national agencies for lunar payload delivery. Venture capital surged to $12 billion in 2023, though consolidation looms as investors prioritize profitability. Challenges, regulatory barriers, supply chain vulnerabilities, and competition from state-subsidized entities like China's Galactic Energy. Chapter 6 Summary: The 21st century space race is no longer a binary contest but a mosaic of collaboration and competition. While CLPS and ESA partnerships highlight the power of shared goals, China's ascendancy and startup dynamism inject fierce rivalry into resource access and technological dominance. Startups, though fragile, drive democratization, yet their survival hinges on navigating a fractured regulatory landscape. As nations and corporations chart divergent paths to the stars, the question remains: will cooperation or competition define humanity's future in space? The next chapters delve into the technologies and policies that may tip the balance. Chapter 7: Emerging Technologies in Space Exploration. The next frontier of space exploration hinges on breakthroughs that transcend traditional rocketry and human ingenuity. From harnessing nuclear reactions for faster travel to leveraging extraterrestrial resources and artificial intelligence, this chapter explores the cutting-edge innovations poised to redefine how we explore and inhabit the cosmos. 7.1 Nuclear Thermal Propulsion, NTP. Nuclear thermal propulsion, long confined to theoretical studies, is gaining traction as a solution for rapid interplanetary travel. How it works: NTP systems use a nuclear reactor to heat liquid hydrogen propellant, expelling it through a nozzle to generate thrust. Offers 2-3x higher specific impulse, ISP, than chemical rockets, enabling Mars transit times of 3 months, versus 6-8 months. Historical context: NASA's NERVA program, 1960s-1972, proved NTP's feasibility but was shelved due to cost and Cold War priorities. Draco project, 2023. DARPA and NASA's joint effort to demo a nuclear thermal rocket in orbit by 2027. Challenges: radiation shielding, protecting crews from reactor emissions. Public perception: overcoming stigma around nuclear systems. Regulatory hurdles: launch approvals for radioactive materials. Future applications: cislunar logistics, crewed Mars missions, and fast transit to the outer solar system. 7.2 In situ resource utilization, ISRU. ISRU transforms extraterrestrial materials into fuel, water, and building supplies, key to sustainable off-world presence. Lunar ice mining, Viper rover, NASA, 2024. Mapping water ice at the Moon's south pole for future extraction. Blue Origin's Blue Alchemist, electrolyzing lunar regolith to produce solar cells and oxygen. Mars methane production, SpaceX's Starship architecture relies on the Sabatier reaction to synthesize methane, CH, from Martian CO and water. 3D printed habitats, ICON's Project Olympus, partnering with NASA to 3D print lunar bases using regolith-based ink. Challenges: energy-intensive processes requiring robust power systems, e.g., compact nuclear reactors. Dust mitigation, lunar regolith is abrasive and hazardous to equipment. 7.3 AI and autonomous systems in mission control. Artificial intelligence is revolutionizing mission planning, real-time decision-making, and spacecraft autonomy. Autonomous navigation, ESA's JUICE mission, AI algorithms guide the spacecraft through Jupiter's complex gravitational fields. Perseverance rover uses auto-NAV to self-drive on Mars, avoiding obstacles without Earth-based commands. Predictive maintenance, SpaceX's Starlink satellites employ machine learning to anticipate component failures and adjust orbits. Data analysis, AI sifts through petabytes of telescope data, e.g., James Webb, to identify exoplanets or cosmic anomalies. Ethical and technical risks, over-reliance on AI in life-critical systems, e.g., crewed missions. Cybersecurity vulnerabilities in autonomous spacecraft. Chapter 7 Summary, Nuclear propulsion, ISRU, and AI are not mere upgrades, they are paradigm shifts. NTP could shrink the solar system, ISRU might end our dependence on Earth-bound supply chains, and AI promises to turn spacecraft into self-reliant explorers. Yet each innovation carries existential risks, nuclear mishaps, resource overexploitation, and autonomous system failures. As these technologies converge, they challenge us to rethink not just how we explore space, but why. The final chapters examine how humanity might balance these tools with the responsibility of stewardship on Earth and beyond. Chapter 8, Sustainability in Space Operations. As humanity expands its footprint beyond Earth, sustainability transitions from an ideal to an imperative. Orbital debris threatens access to space, toxic propellants endanger ecosystems, and long-term habitats demand self-sufficiency. This chapter examines strategies to ensure space exploration's longevity, balancing ambition with stewardship of the cosmos and our home planet. 8.1 Debris mitigation strategies. With over 36,000 tracked debris objects in orbit, sustainability begins with curbing the tragedy of the commons in space. Active debris removal, ADR, ESA's Clear Space 1, 2026, a pioneering mission to capture and deorbit a 112 kg Vega rocket fragment using robotic arms. Japan's ADRASJ, 2024, inspecting and nudging derelict satellites into graveyard orbits via proximity operations. Passive measures, 25-year rule, international guidelines mandate deorbiting satellites within 25 years of mission, and though compliance remains uneven. Design for demise, components that burn up during re-entry, e.g., SpaceX's Starlink satellites use aluminum alloys to minimize debris. Collision avoidance, SpaceX's automated maneuvers, Starlink satellites autonomously adjust orbits using AI-driven risk assessments. LEO coordination, the U.S. Space Force's Space Fence radar network tracks debris down to 10 centimeters, alerting operators to collision risks. Challenges, ADR costs, $10M per satellite, and legal ambiguities over ownership of defunct objects. 8.2 Green propellants and eco-friendly practices. Traditional hydrazine fuels are carcinogenic and ozone depleting. The shift to greener alternatives is accelerating. Hydrogen peroxide, HTP, non-toxic and decomposes into water/oxygen. Used in UK's Skyrro launch vehicles. AFM 315E and LMP 103S, high-performance green monopropellants tested in NASA's GPIM and DLR's OHB Spacelink. Methane, CH, adopted by SpaceX, Starship, and Relativity Space, Terran R, for cleaner combustion and Mars compatibility. Emission impacts, soot from solid rockets, particles from boosters like Ariane 5 SP120 can linger in the stratosphere, accelerating ozone depletion. Electric propulsion, ion thrusters, e.g., SpaceX's Hall effect thrusters for Starlink, reduce reliance on chemical fuels for station keeping. Regulatory push, the FAA now incentivizes green propellants through streamlined licensing and tax breaks. 8.3 Long-term habitat viability. Sustaining human life in space requires closed-loop systems and resilience against extreme environments. Life support innovations. NASA's Advanced Closed-Loop System, ACLS, recycles 98% of water and scrubs CO on the ISS, a model for lunar/Mars habitats. Veggie and acroots. Hydroponic systems grow crops in microgravity, addressing nutritional and psychological needs. Radiation mitigation. Regolith shielding. ESA's Luna facility tests 3D printed lunar habitats using simulated moon dust as a radiation barrier. Active magnetic fields. Conceptual designs for spacecraft with mini magnetospheres to deflect solar particles. Psychological resilience. High seas. Hawaii analog missions simulate isolation stressors, informing habitat design, e.g., private crew quarters, VR windows. Case study. Mars Dune Alpha, 2023. NASA's 3D printed habitat at Johnson Space Center evaluates crew dynamics during year-long simulations. Chapter 8 Summary. Sustainability in space is not optional, it is existential. Debris mitigation preserves orbital highways, green propellants protect Earth's atmosphere, and closed-loop habitats extend humanity's reach. Yet, these efforts face economic, technical, and political headwinds. As nations and corporations race to exploit space resources, the lessons of Earth's environmental crises loom large. Without deliberate stewardship, the final frontier risks becoming another casualty of short-term thinking. The next chapters explore how economics and ethics will shape this precarious balance. Chapter 9, The Economics of Space Travel. The commercialization of space is no longer science fiction, it is a multi-billion-dollar industry reshaping global markets. From slashing launch costs to monetizing orbits and selling tickets to the edge of space, this chapter dissects the financial engines driving humanity's off-world ambitions and the risks lurking beneath the hype. 9.1 Cost reduction via reusability and 3D printing. The economics of space travel hinge on lowering the cost to orbit, enabling new markets and missions. Reusability revolution. Falcon 9's cost per kilogram dropped from $4,000/kg, expendable, to $1,500/kg, reused. Starship's aspirational goal, $10/kg via full reusability and mass production cheaper than air freight. 3D printing efficiency. Relativity Space claims 3D printing reduces part count by 100x and production time by 10x compared to traditional methods. Rocket Lab's Archimedes engine for Neutron uses printed components to cut costs by 50%. Challenges. High upfront R&D costs, e.g., SpaceX spent $5 billion developing Starship. Scalability limits for niche materials, e.g., specialized alloys for printed engines. Impact. Affordable access unlocks smallsat markets, academic research, and asteroid mining feasibility studies. 9.2 Satellite megaconstellations and revenue models. Satellite constellations are the cash cows of the new space economy, but sustainability concerns loom. Key players: Starlink, SpaceX 5,400 plus satellites, 2023, generating $3 billion annually from 2 million subscribers. OneWeb, 648 satellites for global broadband, pivoting to B2B after bankruptcy and UK bailout. Kuiper, Amazon plans to deploy 3,236 satellites by 2029, targeting AWS integrated cloud services. Revenue streams, direct-to-cell, Starlink's partnership with T-Mobile to eliminate dead zones. Earth observation, Planet Labs sells daily imagery to agriculture, insurance, and governments. Risks, market saturation, over 50 proposed constellations compete for limited radio spectrum and orbital slots. Debris liability, insurers demand higher premiums as collision risks grow, e.g., 2023 near miss between Starlink and China's Tiangong. 9.3 Space tourism, market potential and risks. Once a billionaire's playground, space tourism is inching toward mainstream viability, but challenges persist. Suborbital tourism, Virgin Galactic, $450,000 tickets for 90-minute flights, 800 plus reservations despite 2023 safety pause. Blue Origin's New Shepard, 32 km altitude hops, paused after 2022 engine failure during uncrewed flight. Orbital and Beyond, Axiom Space, $55 million seats on SpaceX Crew Dragon to the ISS, SpaceX's Starship lunar flyby, Dear Moon Project, 2025, offers artist-influencer tickets to loop the moon. Market realities, niche demand, UBS estimates $3 billion annual revenue by 2030 dwarfed by satellite broadband, $47 billion. Ethical backlash, critics decry emissions, e.g., Virgin Galactic's hybrid rocket emits 27 tons of CO per passenger. Future models, orbital hotels, e.g., Voyager stations plan 2027 debut. Net zero tourism using green propellants, e.g., hydrogen peroxide. Chapter 9 Summary, Space economics thrives on a paradox, cutting-edge technology enables affordability, but profitability depends on scaling high-risk ventures. Reusability and 3D printing are reshaping supply chains, mega-constellations are monetizing the skies, and tourism dangles the allure of democratized access for those who can pay. Yet, unchecked growth risks repeating Earth's boom-bust cycles in the cosmos. As investors chase orbital dividends, the industry faces a reckoning: will space become a sustainable marketplace or a speculative bubble? The final chapters envision the road ahead. Chapter 10, Future Horizons, 2030 and Beyond. By 2030, humanity's foothold in space will no longer be tentative but transformational. Interplanetary infrastructure, permanent settlements, and next-generation communication systems will redefine our relationship with the cosmos. This chapter envisions the technologies, collaborations, and ethical frameworks that could shape the next era of space exploration and the challenges that could derail it. 10.1 Interplanetary infrastructure projects the Solar System's first interplanetary highway is taking shape, with critical nodes enabling sustained exploration. Lunar Gateway, 2030's NASA's orbiting outpost will serve as a staging ground for lunar landings, Mars missions, and deep space telescopes. Partnering with ESA, JAXA, and SpaceX, its modules include Propellant Depot, refueling Starship and other landers using water ice mined from the Moon. Deep Space Lab, studying cosmic radiation effects on biology and materials. Mars Transit Network, Starship tanker fleet, SpaceX plans annual cargo missions to pre-deploy habitats and methane production plants on Mars. Nuclear tugboats, NASA and DARPA's Draco-derived reactors could tow cargo between Earth and Mars orbits. Asteroid mining proving grounds, startups like Astroforge aim to test extraction of platinum group metals from near-Earth asteroids by 2035, leveraging SpaceX ride-shares. Challenges, financing multi-trillion-dollar infrastructure and ensuring equitable access amid geopolitical rivalries. 10.2 Human colonization roadmaps. Permanent settlements are no longer sci-fi, they're strategic goals with diverging visions. Moon First, NASA/Artemis, Artemis Base Camp, 2030s a South Pole habitat supporting 4-person crews, powered by compact nuclear reactors and supplied by CLPS landers. ESA's Moon Village, an open architecture for international science and tourism. Mars Direct, SpaceX, Mars Base Alpha, 2040s a self-sustaining colony of 1,000 plus using ISRU to produce oxygen, methane, and construction materials. Early focus on sealed biodomes and radiation-shielded lava tubes. Free space habitats, Blue Origin/Orbital Reef, O'Neill cylinders, 2050s rotating space station simulating Earth gravity, built using lunar and asteroid resources. Ethical flashpoints, planetary protection, balancing microbial contamination risks with colonization urgency. Labor rights, debates over corporate governance in off-world settlements. 10.3 Quantum communication and deep space networks. Legacy radio systems will give way to quantum-enabled networks, overcoming the latency and bandwidth limits of deep space. Quantum key distribution, QKD, NASA's Deep Space Quantum Link, 2035 secure Earth-Mars communication using entangled photons, resistant to interception. Lunar Quantum Network, ESA's Moonlight initiative integrates QKD for lunar surface operations. Laser Communication Relays, Solar System Internet, a network of relay satellites, e.g., NASA's Psyche mission optical terminals, enabling 100x faster data rates for Mars rovers and outer planet probes. AI-driven autonomous networks, self-healing protocols for spacecraft swarms, e.g., Dragonfly's Titan mission, to maintain connectivity despite signal delays. Breakthroughs needed, miniaturizing quantum repeaters and hardening systems against solar flares. Chapter 10 Summary, the 2030s will test whether humanity can transition from visiting space to inhabiting it. Interplanetary infrastructure demands unprecedented collaboration, colonies require ethical guardrails, and quantum networks must overcome physics itself. Yet, the pieces are falling into place: Starship's cargo holds, lunar ice deposits, and entangled photons each hint at a future where Earth is not humanity's sole home. As this book's conclusion will argue, realizing this vision hinges on learning from our past, balancing the hunger for exploration with the wisdom to preserve the cosmos we seek to claim. Chapter 11, Conclusion, the path forward as we stand on the precipice of a new era in space exploration. The lessons of the past and the innovations of the present converge to chart a course for humanity's future among the stars. This final chapter synthesizes the themes of frontiers of space technology, innovations and beyond, offering a roadmap that balances ambition with wisdom, nurtures talent, and fosters global unity in the quest for a multiplanetary existence. 11.1 Balancing Innovation with Responsibility. The meteoric rise of private space enterprises like SpaceX and Relativity Space has redefined what is possible, yet their rapid progress underscores the need for ethical stewardship. Innovations such as reusable rockets and 3D printed engines promise cost reduction and scalability, but they also pose risks: orbital debris, environmental impact, and resource exploitation. Regulatory frameworks. The FAA's evolving launch licensing and the Artemis Accord's emphasis on sustainable lunar exploration exemplify efforts to harmonize innovation with accountability. Sustainable practices, lessons from Earth's environmental crises must guide space operations. Initiatives like debris mitigation, e.g., ESA's Clear Space One, and green propellants, methane, hydrogen peroxide, set precedents for eco-conscious exploration. Ethical considerations. As SpaceX eyes Mars colonization, planetary protection protocols and equitable resource sharing remain critical to avoiding the pitfalls of terrestrial exploitation. Quote, Elon Musk's vision of making humanity a multiplanetary species must coexist with Arthur C. Clarke's admonition: the limits of the possible can only be defined by going beyond them into the impossible responsibly. 11.2 Inspiring the next generation of engineers. The future of space technology hinges on cultivating a diverse, skilled workforce. Emerging fields like quantum communications, in situ resource utilization, ISRU, and AI-driven autonomy demand fresh perspectives and interdisciplinary collaboration. Education and outreach. Programs like NASA's STEM internships, the European Space Agency's young graduate trainees, and SpaceX's live-streamed launches ignite curiosity and demystify space careers. Role models and diversity. Figures like Gwynne Shotwell, president of SpaceX, and Dr. Shion Proctor, geoscientist and Artemis astronaut, exemplify the importance of representation in inspiring underrepresented groups. Academic partnerships. Universities are pioneering labs for space tech, such as MIT's collaboration on nuclear thermal propulsion and Stanford's research into AI for deep space navigation. Case study: the 2023 million Argentine pesos Dune Alpha habitat simulation engaged student teams worldwide, blending education with hands-on problem-solving for Martian living. 11.3 Unified Goals for Humanity's Multiplanetary Future. The dichotomy of international competition and collaboration defines our path forward. While geopolitical rivalries persist, projects like the Lunar Gateway and the James Webb Space Telescope demonstrate the power of shared ambition. Global collaboration, the Artemis Accords, signed by over 30 nations, provide a framework for peaceful lunar exploration, though inclusivity gaps remain. Ethical colonization, as China's Tiangong station and India's Chandrayaan-3 lunar mission expand access to space, equitable governance models must ensure benefits extend beyond superpowers. Preventing conflict, the dual-use nature of satellite technology, e.g., Earth observation for both disaster response and military targeting, necessitates robust treaties to avert space militarization. Vision, a future where lunar bases, Martian cities, and asteroid mining ventures operate under a unified charter akin to the Antarctic Treaty prioritizing science, sustainability, and shared prosperity. Final call to action. The journey from Sputnik to Starship has been one of audacity and ingenuity. Yet, the next chapter demands more than technological prowess. It requires a collective commitment to responsibility, education, and unity. Policymakers must craft forward-thinking regulations, educators must empower diverse minds, and industry leaders must champion sustainability. As we gaze toward 2030 and beyond, let us ensure that our multiplanetary future is not just a testament to human achievement, but a legacy of wisdom for generations to come. In the words of Carl Sagan, the sky calls to us. If we do not destroy ourselves, we will one day venture to the stars. Let that venture be guided by the best of who we are. End appendices. Appendix A, Timeline of Key Launches, 2020-2023, December 2020, Starship SN8 completes a high-altitude test flight with a dramatic belly flop maneuver, though it crashes on landing. February 2021, NASA's Perseverance rover lands on Mars, deploying the Ingenuity helicopter. December 2021, James Webb Space Telescope launches aboard an Ariane 5, ushering in a new era of deep space observation. November 2022, Artemis I, NASA/SLS, successfully orbits the Moon, testing systems for crewed missions. March 2023, Relativity Space Terran 1 becomes the first 3D printed rocket to reach space but fails to achieve orbit. April 2023, SpaceX Starship *S first orbital test flight ends in a controlled termination after stage separation anomalies. July 2023, India's Chandrayaan-3 lands near the Moon's south pole, making India the fourth nation to achieve a soft lunar landing. November 2023, Starship's second test flight achieves stage separation but loses contact during ascent. Appendix B, Glossary of Technical Terms, Additive Manufacturing, 3D printing layer-by-layer construction of components using materials like metal alloys, reducing part count and production time. In situ resource utilization, ISRU harvesting and processing extraterrestrial materials, e.g., lunar ice, Martian CO, for fuel, water, or construction, methalox, a rocket propellant combining liquid methane, CH, and liquid oxygen, LOX, favored for reusability and Mars compatibility. Orbital debris, defunct satellites, spent rocket stages, and fragments posing collision risks in Earth's orbit. Quantum key distribution, QKD secure communication method using quantum entangled photons to prevent eavesdropping. Reusable rocket, a launch system designed for multiple flights, lowering costs, e.g., SpaceX's Falcon 9, Starship. Specific impulse, ISP measure of rocket fuel efficiency, analogous to miles per gallon for engines. Appendix C, Profiles of leading space technology firms. SpaceX, Focus, reusable rockets, satellite megaconstellations, Mars colonization. Key tech, Starship, Falcon 9, Starlink. Achievements, first privately funded crewed orbital flight, 2020, over 200 successful booster landings. Relativity Space, Focus, 3D printed rockets, in-space manufacturing. Key tech, Terran 1, Terran R, Stargate printer. Achievements, first 3D printed rocket to reach space, 2023. Blue Origin, Focus, lunar landers, orbital habitats, suborbital tourism. Key tech, New Glenn, Blue Moon, orbital reef. Achievements, first reusable suborbital rocket, New Shepard, 2015. Rocket Lab, focus, small satellite launches, spacecraft components. Key tech, electron, photon, neutron. Achievements, first helicopter catch of a returning rocket booster, 2022. NASA, focus, deep space exploration, lunar and Martian science. Key programs, Artemis, commercial lunar payload services, CLPS, Mars sample return. China National Space Administration, CNSA, focus, lunar exploration, space station operations. Key tech, Chang'e lunar rovers, Tiangong space station. Achievements, first Farside moon landing, 2019, autonomous Mars rover, Zhurong, 2021. End of appendices. This section provides readers with quick reference tools to contextualize the book's themes, from major milestones to the pioneers driving innovation.